So in the last video, we defined the chain groups CRK for abstract simplicial complex K. But we wanted to make these into a chain complex. To make them into a chain complex, we need to define the differential, d from CRK to CR minus 1K, and we need to prove that d squared is 0. So in this video, we're going to give the definition of d and some examples, and then in the next video, we'll prove that d squared is 0. So here's how we define the differential. So remember, a typical element of the group CRK can be written as pointy brackets V0 up to VR, where these are V0 up to VR, they're the list of vertices of some simplex given in a particular order. And to apply dr to that, what we do is we go through the list of vertices, and we look at all the simplices that we can get just by leaving out one of the vertices. Okay? So we leave out the vertex vi, then that gives us an element of CR minus 1k, and it turns out that we have to multiply that by minus 1 to the power I. Okay? So then we take the sum of those from I is 0 up to R. Okay, so let's see how this works in the case R equals 3. So a typical generator of the group C3K is like this, pointy brackets V0, V1, V2, V3. And to apply D3 to that, here we've got the term where we omit V0, here's the one where we omit V1, here's the one where we omit V2, and here's the one where we omit V3. And this first one comes with a sign plus, then minus, then plus, then minus. Okay, and then just writing this out without the grayed out vertices, here we get V1, V2, V3, minus V0, V2, V3, plus V1, V0, V0, V1, V3, and minus V0, V1, V2. And as we've mentioned before, it's often good to use this kind of abbreviated notation. So instead of this pointy V0, V1, V2, V3, we just write 0, 1, 2, 3. And then for this term here, we just write 1, 2, 3 with the 0 missing. For this term here, we just write 0, 2, 3 with the 1 missing. This one, 0, 1, 3 with the 2 missing. And here, 0, 1, 2 with the 3 missing. And again, the signs are plus, minus, plus, minus. Okay, so that tells us what to do with the basis elements for C3K. But if we've got a linear combination, then we just apply it to each term, right? So for example, we could have a chain written in this abbreviated form as 3abc minus 4bcd, and you want to apply d2 to that. Well, you just get 3 times the d2 applied to this abc minus the 4 times the d2 applied to the bcd. And we just work that out. So here for the ABC, we've got this term with the A missing, then with the B missing, then with the C missing. And then here with the BCD, here with the B missing, then here with the C missing, and then there with the D missing. And we just do a little algebraic simplification. We got the minus 4BC cancelling against the 3BC there, and then otherwise everything is just separate. So we get a minus BC, minus 3ABC, minus 3AC, plus 3AB, minus 4CD, plus 4BD. Okay. So one thing we glossed over just a little bit, we've got this special sign rule for dealing with the generators of C3K, and we need to check that our definition of D is consistent with that. Okay. So we've got a sign rule which says that if you apply a permutation, then the generator of CRK changes according to the sign of the signature of that permutation. Now, in the permutation group, the simplest kinds of permutations are these adjacent transpositions, tor I, that just sort of exchange the ith and I plus first entries in your list. And it's a standard fact about the permutation group that I hope you remember, that these adjacent transpositions, they generate the full permutation group. And because of that, it's going to be enough to check that our definition of D is consistent with the action of these adjacent transpositions, tor I. So we'll only go in detail through just one particular example, where you've got a 5 chain, say V0, V1, V2, V3, V4, V5, or 0, 1, 2, 3, 4, 5. And then we can apply this adjacent transposition tor3, which swaps the 3 and the 4. And that gives us this new chain U prime, which is 0, 1, 2, 4, 3, 5, the 3 and the 4 the wrong way around. Okay, okay, so according to our rules for C5, U primes counts the same as minus U. And so if everything fits together properly, then if we apply our rule for D5 to U prime, then we ought to get the negative of D5 applied to U. So let's check that out. Okay. So here's D5U. Okay, so U is 0, 1, 2, 3, 4, 5. So here we get the one with the 0 missing, then with the 1 missing, the 2 missing, here with the 3 missing, here with the 4 missing, here with the 5 missing. Okay. Then here we've got D5U prime. Okay, so again we omit the initial entry. It gives us 1, 2, 4, 3, 5. If we omit this entry here, we get 0, 2, 4, 3, 5. We omit this 2 here, we get 0, 1, 4, 3, 5. Now we omit the 4 from there, you get a 0, 1, 1, 2, 3, 5. If you omit the 3, you get the 0, 1, 2, 4, 5. And you omit the 5, 0, 1, 2, 4, 3. So that gives you all the terms in D5U prime. So how do these things line up? Okay, let's look, for example, at the I equals 2 case. I mean, here you've got 0, 1, 3, 4, 5, and here 0, 1, 4, 3, 5. In both cases, the 2 has been taken out. Okay, and so this guy is exactly the same as this guy, except the 3 and the 4 are switched. Okay, so by the sign rule for C4, this one and this one are negatives of each other. So that's what happened for I equals 2, and it works exactly the same for I equals 1 and for I equals 0 and for I equals 5. Okay, I mean, here we've got I equals 5. We've just dropped out the last term in U, and we've dropped out the last term in U prime. That gives us U 0, 1, 2, 3, 4, 0, 1, 2, 4, 3. And by the usual sign rule for C4, because they've got the 3 and the 4 swapped, these count as negatives of each other. But the 3 and the 4 case is just slightly different. Okay, let's look at this term here, 0, 1, 2, 4, 5. Okay, that appears in D5U with the 3 missing, and it also appears in D5U prime. But you know, this occurs at step 3 here, but actually occurs at step 4 in D5U prime, right? So this one comes with a sign -1 to the power 3. This one comes with a sign -1 to the power 4, because this one appears in the I equals 3 slot. This one appears in the I equals 4 slot. So those are negatives of each other. And then similarly for I equals 4, you know, if we leave out the 4 in U, we get this 0, 1, 2, 3, 5. And that appears in slot 4. And exactly the same term appears in D5U prime, but it appears in slot 3. So here it appears with a sign -1 to the 4. Here it appears with a sign -1 to the 3. So these appear with opposite signs, and everything cancels. Okay, so again, so this is minus this is minus this is minus this is minus that, this is minus that, this is minus that. So we see that D5U prime is equal to minus D5U. Which is good. That's how the sign rule is supposed to work out. And so we only went in detail through the case of Tor3 at R equals 5, but if you think about it a little bit, you'll see that it just basically works the same way for any R and any adjacent transposition. And also similar sort of argument that D is compatible with the rule that rule for repeated vertices. So let's have a look how this goes with a boundary of a 2 simplex. Okay, so here we've got 2 simplex ABC, and then D2U. Then we leave out the if we leave out the C. So we leave out the A, you get a BC. You leave out the B, you get a minus AC. You leave out the C, you get a plus AB. Okay, we might prefer to rewrite this slightly. I mean, we've got a minus AC. We could rewrite that as plus CA, and then it's kind of more natural to move that term to the end. So we get a BC. So we get this AB first. Let's write, and then we've got this term BC, and then we've got this minus AC, which you can also write as CA. So now, if we look at it over here, so that's like the AB is going here, and then the BC is going there, and then the CA is going there. So what you see is we're just going all the way around the boundary of this triangle. So over here, we could kind of indicate the direction of this with an anti-clockwise arrow, and then what you get as the boundary is just all the edges appear in this anti-clockwise order as is compatible with the circle that we wrote there. So similarly, we could do this with a 3-chain. consisting, so 3-chain V equals ABCD, so that kind of corresponds to a tetrahedron with vertices A, B, C, and D. You'll find that D3V consists of four faces of tetrahedron oriented in an appropriate way. So there is an interactive demo for that, but I think we'll do that as a separate video. So here's an example of how D2 works out. So here we've got simplicial complex K, and here's a 2-chain U, ABP, BPQP, etc. But this is just the sum of all 7 triangles oriented anti-clockwise. So this term ABP, for example, that's ABP, that's this triangle here, oriented anti-clockwise. This last term DAP, okay, so that's DAP here, that's just this triangle here going around anti-clockwise. Okay. So how does D2 of this work? Okay, so we'll do this twice, on this slide and on the next slide. So this slide, we're just going to do it in a kind of very obvious pedestrian way, just write everything out from the definitions. Okay, so here we look at the differential ABP. So you leave out the A, you get a BP. You leave out the B, you get minus AP. Leave out the P, you get a plus AB. And then for the BQP, again, you leave out the B, you get this QP here. Leave out the Q, you get this minus BP here. Leave out the P, you get a plus BQ there. And you carry on for the rest of the 7 triangles. So that gives us 3 terms for each triangle, 21 terms altogether. Okay. To see what's going on and make sure we collect everything together correctly, it's best to sort of rewrite these terms with everything in alphabetical order. So here, for example, we've got a QP, and we're going to write that as minus PQ. Right, that will just make it easier to keep everything straight. And over here, for example, we've got RQ, we're going to write that as minus QR, and so on. Okay, now when we've done that, we can see the cancellations a bit more easily. So we've got a BP here, for example, and if we look through here, we should find another BP somewhere. Yeah, there we go. There's a plus BP there and a minus BP there. That's cancelling. And you've got a minus AP here, and we work through here. There's a plus AP over there. That's also cancelling out. So it turns out that there's, like I said, we had 21 terms, about 14 of them cancel out in pairs, and what we're left with is just these 7 terms here. And let's just kind of regroup these a bit. So we've got an AB here, and a BC and a CD, and then I've got a minus AD. It's convenient to rewrite that as a plus DA. And then over here, you've got a the minus PQ, I'm going to write as QP, the minus QR, I'm going to write as RQ. So we've written everything, so now the coefficients are all positive. And what does this look like geometrically? Well, these AB, BC, CD, DA, that's basically just going around the outer edge of this square in an anti-clockwise direction. And this QP plus RQ plus PR, that's going around clockwise around the inner triangle. Yeah. Okay, so let's do that same example again, but maybe in a bit more of a conceptual way. Okay, so let's look at this edge RQ here. Okay, so how does this come out when we look at D2U? Okay, so U contains this triangle CRQ going anti-clockwise, like all of them, and RQ appears here as part of the boundary of this yellow triangle here. And it doesn't appear as part of the boundary of any other triangles, so we just end up with a plus RQ in D2U. There's nothing else that can cancel against it. But what about this outer edge on the outer square here from AB? Okay, so that appears again as part of the boundary of this triangle ABP, and again this is going anti-clockwise, and so it runs along in this direction from A to B. So we get a plus AB as part of the boundary of this triangle, and AB doesn't appear as the part of the boundary of any of the other triangles. But let's look instead at one of these kind of internal edges that runs from the inner triangle out to the outer square, like CQ. Okay, so this appears as part of the boundary of two different triangles. So this one is BCQ, this triangle here, BCQ, and that contributes a plus CQ. On the other hand, you've got this triangle here, CRQ, and that contributes a QC, which is the same as minus CQ. So those two cancel out. This appears with a coefficient +1 from one term and a -1 from the other term, and those cancel out. And so we don't see CQ at all in D2U. So the conclusion is that all the, we only did one of the example, we only did one of the inner edges RQ, but they all appear, they all work the same way. So you get all these edges on the inner triangle circulating clockwise. And similarly, all the outer ones behave the same way as AB. You get them all once anti-clockwise, and so we get D2U is the inner triangle clockwise and the outer square anti-clockwise, just as in the on the previous slide. Now we'll just quickly do an example of D1. Okay, so here is another different simplicial complex with vertices A up to I, and here we can have a one chain. It's consisting of AF plus FB plus BC plus CH plus HI plus IE. Okay. So what happens when we do D1 of that? Well, D1 of AF is F minus A, D1 of FB is B minus F, D1 of BC is C minus B, and so on. So we get all these guys here. But you see, most of this cancels. The F here cancels the F there, the B here cancels that B, the C cancels that C, this H cancels that H, this I cancels that I. Everything cancels except for this A minus A here and this plus E here, it's E minus A. And why do we get all this cancellation? It's just because, we've got a chain of arrows all following on from each other, arranged in a consistent direction. So this B, for example, that's going to occur with it occurs with a plus as part of FB, and then as a minus as part of BC, and those cancel out. So that's the way the differential works for this chain of one chains, as we've got in this picture.